Welcome everyone. Today we are diving deep into the concepts of machine learning, which is PAC Learning by Dan Roth. I, Priyamvada from MTech AI IIT Patna, along with my team Shweta Kumari and Manoranjan Singh, have prepared a super interactive slides for you guys to make this topic easy and to understand the concepts easily. Stick around till the end. We have prepared this PPT under the supervision of Professor Arijit Mandal. So, let's see the contents in our slide. First is the introduction part, then the overview of the paper, PAC learning framework, concept learning, hypothesis space, error bound, and sample complexity. Then we will discuss about the strengths and contributions of the paper. Research gap and limitation, applications and real-life example, future research direction, conclusion and references, and in the last we will have Q&A. So, first come to the introduction part. What is computational learning theory? A field of machine learning that studies how algorithms learn from data, focuses on mathematical guarantees for learning models. It helps to answer how much data is needed, how accurate can learning be. See the importance of machine learning. It ensures and generalizes well to new unseen data. It helps to design efficient learning algorithms with limited data. It forms theoretical foundation of for AI and ML application. Let's see the objective of the presentation. We review key concepts from the paper by Dan Roth. We discuss the PAC learning framework and error bounds. Let's highlight the limitations and research gaps in the paper. Then we will explore future research direction in learning theory. Coming to the next slide, overview of the paper. The author Dan Roth, a researcher in machine learning and AI. He is well known for his contributions in computation learning theory. Let's see the summary of the topics we have covered. How many machines learn with limited data? Concept learning and hypothesis space. It selects the best model. Sample complexity and error bound. How much data is needed? Generalization in learning. Making predictions on new data. Key contributions of the paper. It provides mathematical foundations of machine learning, then defines error bound to measure learning performances. It explains relationship between training data and accuracy. Coming to what is PAC learning framework. Let's see about what is PAC learning. PAC learning, probably approximately correct. Learning is a theory that explains how machine can learn from data. It ensures that a model learns accurately with a high probability using limited data. Assumptions in PAC learning. The data comes from fixed distribution. The target concept can be learned by a hypothesis given from a given dataset. The algorithms can efficiently find a good hypothesis. Let's see the role in theoretical machine learning. Helps in understanding how much data is needed for learning, provides a mathematical guarantee for learning success, and it forms the basis of many modern ML algorithms. Let's see a small formula which can help in PAC learning. With high probability, the error of a learned hypothesis H will be within a small margin of a true error. So let's understand it with an example. If a student practices 100 math problems and makes error in 5, the probability of performing well on new test is high. Example, learning to recognize cats. Imagine a child learning what cat looks like. They see many different cats. They form a general idea of cat, that is a hypothesis. If they see a dog and mistakenly think that it's a cat, they adjust their idea. PAC learning ensures the child learns correctly with high probability using limited examples. So, you must have understood PAC learning through this example. Let's compare PAC learning versus modern deep learning. According to the definition, a theoretical framework for machine learning that ensures models are probably approximately correct. On the other hand, deep neural networks that learns patterns from large amount of data without explicit theoretical guarantees. On the basis of goal, PAC learning focuses on to find hypothesis that is approximately correct with a high probability. On the other hand, modern deep learning to train models that generalizes well to unseen data using layers. Mathematical foundation strongly based on the probability theory, sample complexity and VC dimension. On that other hand, modern deep learning based on optimization techniques like gradientation and backpropagation. PAC learning requires well-defined training sample but limited sample complexity. Modern deep learning can handle massive data sets and learn from large-scale unstructured data. On the other hand, PAC learning often computationally expensive due to theoretical concepts. But modern deep learning is efficient due to GPU and TPU acceleration, but can be very expensive for deep architectures. Now Shweta will move forward with the slides for the better understanding.
Hi everyone, I am Shweta. Now we have basic understanding of pack learning. Now let's discuss about concept learning and hypothesis space. What are instance, concept and hypothesis space? Instance space. It's about the set of all data points or set of all inputs, as for example set of all emails, set of all images. What is concept space? It's about the set of all correct answers, as for example email is spam or not spam. What is hypothesis space? The set of all possible models that can predict the concept. Hypothesis means rule or model. How pack learning selects the best hypothesis? It learns from training data to find the most accurate hypothesis. It chooses a hypothesis with the least error on unseen data. It ensures the selected hypothesis is probably approximately correct. Now, discuss about Venn diagram, which illustrate the relationship between instance space, concept space and hypothesis space. Instance space is about the set of all data points or set of all input space. Concept space. This yellow part represents the concept space, this purple part represents the hypothesis space, and this green and purple part intersection represent the intersection of concept space and hypothesis space, which is the good hypothesis. Now let's take the example of sorting fruits by color. Instance space. A basket with apples, bananas and grapes. Concept space. Sorting fruits into red, yellow and green categories. What is hypothesis space? In which we take the different way to group them by color, size and shape. Pack learning helps pick the best way to classify fruits with minimal mistakes. Now let's come to the slide error bounds and sample complexity. Okay, how much data is needed for reliable learning? The more data, the better the model learns. What is sample complexity? Sample complexity tells us minimum number of examples needed. What is upper bound and lower bound on learning? Upper bound means the maximum data required to learn with high accuracy. What is lower bound? The minimum data needed for learning to be possible. What's the relationship between error probability and training size? More training data reduces error probability, which means the more number of data we have, the less will be the error. A small data set can lead to the overfitting and underfitting of the model. Okay, what's the formula for error? Error is equals to misclassified examples upon total number of examples. Let's take an example of if a student answer 8 out of 10 question correctly, then error will be 2 out of 10, which means student incorrectly answers two answers, which means 20% of the answers given by student is incorrect. Now again, takes examples of learning spelling. Okay, a child learns to spell by practicing words. If they only practice few words, they might make mistake on new ones. More practice, more examples, reduce spelling errors. PAC learning ensures enough examples are given to minimize errors. This graph shows the relationship between training size and error probability. And okay, this blue line represents the relationship between training data set size and probability. Uh, as per training data set increases, probability is also increases, and as training data size increases, error rate decreases, which is denoted by red line. You guys can show this red line represent relationship between training data size and error rate. As training data size increases, error rate is decreases. Now let's discuss about strength and contribution of the paper. The first contribution is the formal foundation for machine learning. It establishes theoretical rules for how machine learns, defines key concepts like PAC learning and sample complexity. Second point is provides mathematical guarantees for learning algorithm. It ensures model learns efficiently and correctly with enough data. It uses error bound to measure learning performance. Okay. Third point is explain how model generalizes to unseen data. It shows how model trained on one data set can work on new data. It helps prevents overfitting by setting learning limits. Now Manoranjan will explain further part of this slide.
Welcome back, learners. In our previous slides, we have seen that how PAC learning is related to the machine learning. Now it's time to take a deep dive into it. Our first topic is research gaps and limitations in PAC learning. What the paper lacks means what this paper doesn't have. Application to deep learning. As we all know that PAC learning is designed for simple models. It does not directly explain how modern neural network learns. Point number 2, non-stationary data. In real world, data changes over time by time. For example, stock markets, weather, and almost each and everything. But PHA learning can assume a fixed data distribution which is unrealistic in real life. Number third point, computational complexity. Real world models need efficient algorithms that run on limited resources. So it is computationally so expensive. Okay. Number fourth point, practical implementation. The paper is highly theoretical with a little focus on real world application. Now, we coming back to an example of learning math formulas versus understanding real maths. PSA learning works well with memorizing formulas, but in real life, math problem changes. Example, price, discount, etc. PSA learning assumes fixed rules which may not always apply in real world situation. As in real world situation, PSA learning is not that much helpful. Uses of PSA learning in advanced AI or in real life. Point number 1, optimizing AI models. PSA learning helps train AI models effectively with fewer examples while ensuring the high accuracy. It means PSA learning only needs a fewer examples while it trains the data in high accuracy. Point number 2, self-driving cars, ensuring autonomous vehicle learn safe driving behavior with minimal test cases and high reliability. PAC learning is also used in self-driving cars. Third point, medical diagnosis enhances AI models in detecting diseases. For example, cancer detection. How can be it will helpful in medical diagnosis by reducing errors in predictions. Right. Point number 4, speech and image recognition. Used in AI assistant like Siri, Alexa, and facial recognition system to improve learning efficiently. Our last point is fraud detection. Helps financially AI system identify fraudulent transactions accurately with minimal training data. Now, coming to the future research and directions, where we can go next by this paper. Extending PSA learning to deep learning and reinforcement learning. We have to adapt PSA learning for complex neural networks and AI systems. Point number 2, developing models for real world and non-stationary data. Useful for areas like stock prediction, weather forecasting, and fraud detection, where data always remain changes. Point number 3, reducing computational cost in learning algorithm. Make PAC learning faster and more efficient. The last point is bridging theory with real world ML application. Apply PAC learning to practical problems like in healthcare, in finance, in robotics, and etc. Now, coming to an example, teaching AI to play games. Suppose we have an AI to play chess. A chess playing AI learns from thousands of past games. In PSA learning, it helps us to choose the best move efficiently. Future AI should learn new strategies dynamically, not just from past games. Now coming to conclusion, the summary and key findings. PSA learning provides a theoretical foundation of machine learning. As we all know, that PSA learning provides basically a theoretical foundation of machine learning. It is not that pretend out that we apply it practically. It is now on only on theoretical foundation. It helps to understand how much data is needed and how models generalize. Importance of addressing research gaps. So what is the importance of addressing some research gap which is in these papers? The PSA learning does not fully apply to deep learning and real world examples. As we have discussed earlier, the PSA learning does not fully apply to deep learning. It does not work good with neural networks, as we have discussed earlier. Needs improvement for non-stationary data and computational efficiency. It needs some improvement for the non-stationary, means the data which changes again and again. And it is also, as we have mentioned earlier, it is computationally costly. So we have to make computational efficiency. Now, call to action for future research. Develop a new PSC based model for modern AI. Improve algorithm to handle real world data changes. Now, coming to references. We have taken references from Roth D computational learning theory, valid LGA theory of learnable, etc. You can see here. Now, if you have any doubts or any clarification, please feel free to ask. Comment down your doubts in comment section. I will answer it. Thanks for your time. Welcome back, learners. In our previous slides,